Okay, we may as well get started. I want to answer a question from last time, which was references. So let me just give you some references for this kind of material. The classic reference is a book by Bender and Orzag. It's got a long title. I think it's something like Advanced Math Methods for Scientists and Engineers. I might have got this wrong. But I do remember that it's called Volume 1. It's one of these interesting books that doesn't even have a Volume 2, but it's called Volume 1. Okay? So this is the classic reference. There's another well-known reference by Nefi called more prosaic perturbation methods. So a lot of the context in which I usually learned most of this thing was in the context of fluid dynamics. Most of these methods were invented to solve fluid dynamical problems or electrical engineering problems. And so there's this book by R.S. Johnson, which is, again, got a long title, Modern Theory of Water Waves, something, something. This is a red Cambridge applied math text. So there's a red Cambridge applied math text series, these red books. And R.S. Johnson has one on water waves. Johnson himself is an expert in perturbation methods, so he goes about deriving all these reduced models from one big model in different regimes and so on and so forth. There's a more recent book by Ablowitz called Nonlinear Dispersive Waves. It's got a subtitle as well, Asymptotic Analysis or some such thing. This one is also ditto. One of these red Cambridge applied math textbooks. So Ablowitz discusses water waves. He discusses problems arising in photonics, so optics, that kind of stuff. He's another expert in perturbation methods and how to really exploit perturbation methods to understand what's going on. Oh, yes. So most of this is like really classical stuff. And it's done in this sort of heuristic style where you kind of need to know a little bit about the problem, you need to think a little bit. I do like a set of notes by John Hunter. So if you just Google Hunter method of multiple scales, and to help your search engine, if you add the word math, you'll end up with a PDF, and click that PDF. It'll say something like chapter 6 or something. It's very hard to find from his webpage. It seems like he has written other stuff, but he hasn't given you a direct link, but that Google search certainly works. I've tried it multiple times. He emphasizes a lot about the Fredholm alternative and that sort of perspective. He's a honest-to-goodness mathematician, so he definitely likes taking that perspective. A lot of the other stuff is more traditional, not necessarily emphasizing that, and sort of presenting a plethora of techniques that seem different. Especially Bender and Orszag, the classical text, will do boundary layer theory, WKB, and method of multiple scales. And really, method of multiple scales sort of subsumes everything else. WKB you may have seen in a quantum mechanics course or somewhere else. That's a special case of method of multiple scales. If you are an engineer and you know something about homogenization, so if you've got a medium with like defects on one order and structure on another order, how do you get effective equations? It's again, method of multiple scales uses again this Fredholm type alternative argument. All right, so I mean, I would definitely suggest this as a good reference. They're all wonderful, beautiful books that you should read at some point. Okay, so with that, I want to continue talking about nonlinear PDEs, and the nonlinear PDE for today is a weakly nonlinear shallow water wave model. So sometimes this is called the Boussinesg system. Many equations are called the Boussinesg system, so this is one of them. So this is derived from the, let's say, Euler equations for fluid flow. Right, so that's Navier-Stokes with no viscosity. And then you assume irrotational flow. And you also assume shallow water, and you assume weakly dispersive and weakly nonlinear. So this is for fluid flow, let's say with a free surface. Right, so imagine a thin layer of fluid with a free surface, and what you want to describe is how does the height change, and what is the average, vertically averaged horizontal velocity. Right, so there's just one horizontal velocity, and you look at the vertical average of that. Yeah. Weakly dispersive, actually, let me just write down the equation and you'll see what I mean. So what is the Boussinesg system? It's ddt eta u plus 0, 1, 1, 0 ddx eta u plus epsilon uxxx by 3 plus dx u eta ux. So it has the usual structure, some linear operator plus epsilon times something, but notice there's a linear term multiplying an epsilon. There's this high derivative, this third order derivative that multiplies an epsilon. So this higher order derivative leads to dispersion in the system, and since I have an epsilon that's multiplying both my nonlinearity and the dispersive term, the higher order derivative, these two are the same order, nonlinearity and dispersion, I have this weak nonlinearity and weak dispersion. Right? So it's not just an issue of scaling the unknown field by an epsilon, I've also somehow stretched x. Right? Because if I just scaled u to epsilon u, eta to epsilon eta, this term would have not got an epsilon. The fact that it has an epsilon is the fact that it has higher derivatives. So what you also need to do is scale x and t by 1 over epsilon. And so then this third order derivative is smaller than this first derivative in x. Right, so to get the system, you need to assume small amplitude and long behavior. So derivatives are smooth. You have a question? Yeah, so physically speaking, eta represents the height of the fluid column. And u is the horizontal velocity. Since there are no z derivatives, this typically means the vertically averaged physical velocity. Right? And that's true for a lot of shallow water models, right? For shallow water equations, the horizontal field is actually a vertically averaged field. All right, so this is our Boussinesg system. It's of the form Lz plus epsilon n of z, where n is not really nonlinear, because it's the linear part. And we're going to do the same thing as always. Might as well give you this. Epsilon is like a h over L squared. So h is a typical depth, and L is a typical length. So if you want to think about it, it's actually a good way to think about it. So if we started off with the original problem, we had to do a series of steps to arrive at this equation. We actually assumed that the original problem represented horizontally periodic solutions. And that period is L. And we had to assume that the typical depth of the fluid was small compared to that horizontal period. That typical depth is h. And so this epsilon is actually an h over L squared. It's like an aspect ratio squared. Okay? Of course, at the level of this PDE, this is just a small number, right? You don't really care at that level what epsilon meant. Okay, so I'll still call it the linear operator, but I mean, keep in mind I'm really interested in the order 1 linear operator. L is ddt plus 0, 1, 1, 0 ddx. Okay, and I need to know its null space. I would also want to know its adjoint and the null space of the adjoint. Okay, so what is the null space of this? So first of all, just note 0, 1, 1, 0 is a real symmetric matrix with eigenvalues plus or minus 1 and eigenvectors 1, 1, 1, minus 1, respectively. I'll leave that for you to convince yourself that these are indeed the eigenvalues, the eigenvectors. So if I were to write this symbolically, where A is this, then I have AV is lambda V, where V is the eigenvector matrix, lambda is the diagonal with the eigenvalues. Yes? Sorry, can you say that again? I didn't hear that. So why is the small parameter square of something else? If I showed you the derivation, you would know why. So it comes from another PDE, a calculation, and then that small parameter is actually h by L squared. So I didn't answer your question, but it's like, read Johnson's book. He'll tell you why. Okay, so with this, we can consider L eta u 0, I can write in the following way using the decomposition. What is it? So that is V inverse lambda V ddx. Eta u. Right, I just did the spectral decomposition. So instead of A, I put it spectral decomposition. Now, V, lambda, and V are all constant matrices, so I can obviously multiply both sides by V. If I multiply both sides by V and suggestively write it V eta u in that way. Right? Now, I want to solve for eta u. Remember, V is an invertible matrix. So what I really just need to solve for is V eta u, which is to say I want to just know the null space of this operator. But the nice thing about this operator is it's diagonal. So lambda is a diagonal matrix. So this thing is nothing but t plus ddx, ddt minus ddx. Right? It's a diagonal operator, which means I can solve each line independently. And the null space of the first one is profiles advecting to the right. The null space of the second one is profiles advecting to the left. So to summarize, this is just equivalent to saying V eta u should be f of x plus f of x minus t 1 0 plus g of x plus t 0 1 for arbitrary functions f and g dictated by the initial condition. Right? And you can multiply an extra, possibly this should be V inverse. Yeah, anyway. The point is we can now get U and eta V inverse acting on all of that junk, which would just be the first column of V inverse and the second column of V inverse, times that same scalar function, f or g. Right? Everyone okay with this so far? So the advantage of knowing that this was a real symmetric matrix is I know it's diagonalizable. If it's diagonalizable, then I have this spectral decomposition. Once I have the spectral decomposition, I can turn it into a sequence of uncoupled problems. Once it's uncoupled, I know how to solve. Then I can go back and sort of do the inverse transform. I mean, this is literally how you would have solved other systems as well, but I'm just doing it in a more abstract way. You can also see that I could have actually replaced this by any real symmetric matrix. It didn't have to be this particular one. Moreover, if you read everything from this line onward, it doesn't even have to be a two-dimensional system. It can be an n-dimensional system, so long as it's a real symmetric matrix that you're dealing with, right? ddt plus real symmetric matrix ddx. It can be an n by n system. That's perfectly fine. Yes? Oh, sorry. Maybe I wrote this the wrong way. This should have been V lambda. And then this is that. Now I'm much happier. Yeah. Yes? SVD for a square matrix is eigenvalue decomposition, really. If it's not diagonalizable, you really go to the Jordan form. Don't go to the SVD. Go to the Jordan normal form, because what you're really interested in is the generalized eigenvectors as well. You are interested in filling the space with enough eigenvectors, but you have to pull in the generalized eigenvectors. So for a number of problems that I've seen, usually you end up with a real symmetric matrix for very good physical reasons. That some quantity has to be like a positive quadratic invariant or some such thing. So there's an energy that you need to define. When you have these degenerate directions because of the absence of enough eigenvectors, you get these null directions where you're not sure whether the energy is positive definite. It might just be positive. There could be like zero directions and whatnot. So, and remember also when you did first order systems of differential equations, ODEs, you know that the solutions when you have these degenerate eigenvalues which are missing which are missing eigenvectors, you get these combinations of e to the lambda t and t e to the lambda t. So you can get algebraic growth in time. And that's something to worry about if you are dealing with, specifically if you're dealing with non-normal matrices here. If you're dealing with symmetric matrices, which are a specific case of normal matrices, then you're perfectly fine. And if you followed the derivation, which I didn't show you, you realize that this really has to be a real symmetric matrix for physical reasons. Okay. But that is a good question, that in general, what do you do? Actually, in a problem with Manas, we do look at that case, like what happens to that. You can still do perturbation theory, you just have to be a little careful about how you're doing perturbation theory. Okay, so we can write this, in other words, as f of x minus t 1, 1, g of x plus t 1 minus 1. Right, that's my general solution. Notice where the eigenvalue went. The eigenvalue goes into setting the coordinate frame for the profile. So if you have a higher dimensional system, you'll have more eigenvalues, and then that means you'll have more speeds. So you'll have profiles going in different directions at speeds dictated by the eigenvalues. Okay? So this is our linear operator. Let's stick to or impose 2 pi periodic functions for the operator L. Now I can just say it's 2 pi periodic because in x and t it'll be the same period. So f is the function that's 2 pi periodic. G is the function that's 2 pi periodic. So it's 2 pi periodic in x and 2 pi periodic in t. So, and since it only appears in this combination, I can actually just deal with one profile variable, not with an x and a t. I can just deal with the combination x minus t or x plus t independently. Right? So I have an inner product for x minus t and an inner product for x plus t. And a function that depends on x plus t doesn't even belong to the space of x minus t functions. Right? They're kind of orthogonal because they're not in the range. Okay? All right, very good. So I can define an inner product let's say z tilde z to be 0 to 2 pi, 0 to 2 pi, eta tilde eta plus u tilde u in terms of x and t, which would certainly be true whether I had chosen x plus t or x minus t. Both are 2 pi periodic functions, and I can do this. If I wanted to do just x plus t and x minus t, I basically have to do a change of variables to the x plus t, x minus t variable. So you'll get some Jacobian, which will be 1, and then, that's the coordinate I can use. I think in the exercise, I make you do everything in the traveling frames as well. Okay. With this definition, we find the adjoint just to be negative L. Right? It's a real symmetric matrix, so the transpose didn't hurt it, and then the derivatives turn into negatives, and so L dagger turns out to be minus L, which means L dagger and L have the same null space. Right? So both of them are spanned by expressions of the following form. Once again, we have a two-dimensional null space, so when we go to the perturbation theory, we're going to say, let me just consider rightward traveling waves. I could repeat the entire exercise for leftward traveling waves. This is entirely what I did when I did consider e to the I kx minus I omega t for fixed k. It was true for all k, I picked a certain k. I have a statement for all eigenvalues, I'll pick one of the eigenvalues and tell you how things change. Does that make sense? Yeah? Okay, so we begin the perturbation series. Eta u, eta naught u naught, plus epsilon eta 1 u1. And the fact that I wrote plus dot 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 means I only have to do one Fredholm alternative today. I don't have to do two, okay, to get an interesting result. Okay, so the order 1 equations are nothing but this. Which then says we can write down, we can take, this is not the general solution, but we're assuming that this looks like x minus t 1, 1. Right? Now, as always, when I want to go to the next order, I have to set something that was a constant at the previous order to start depending slowly on time. What is constant at the lowest order? The shape of the profile, which is to say the initial condition for these guys. So f was initially a function, and it was a fixed function that translated. Now I'll allow that function to change in time. At what order of time? Well, I have an epsilon here, so I'm going to get these terms at the next order, evaluated at the 0th order, and I'll start modulating time. So I'll have a slow time scale, an epsilon t, to balance these things. Yes, explicit t dependence. So what I'm going to do is say, so you are in the traveling frame of reference, and then things start changing in that frame of reference. So if you wanted to know what the physical speed is, well, you have to take into account both. The original eigenvalue plus whatever other corrections due to the fact that things are changing in that time speed. Right? Do you have a question? Yes. Yes, that's right. That's right. Correct. Correct. Because what I really have is, yeah, it's sort of like the best way to write down what the null space is, this, as opposed to a Fourier decomposition. You could write down a Fourier decomposition, and then your Fourier decomposition will be e to the ik, parentheses, x minus t. So then you realize, oh, it's really just a function of x minus t, and I can actually do this Fourier integral. For a dispersive problem, I don't know how to write down the integral. Right? So it really comes down to the fact that if I had e to the ik x minus t some f hat k, I can use the Fourier transform to write this as f of x minus t. But suppose instead we had ikx minus ik cubed t. I don't know how to do that integral as a generic function of x and t. And since I don't know how to do something, I don't do it, and I stick with individual Fourier modes. Right? What do you mean by the solutions are equivalent? Ah, yeah. Yeah. Yes. Because you're effectively assuming a special form for this, but you're still going to modulate it. And you'll end up with that amplitude of the sine wave satisfying something like this, but the only messy bit is going to be this plus the complex conjugate sort of bit. Yeah. Now, if you are generally playing the game with plane waves, you may not want to have weak dispersion. Elevate this weak dispersion to a strong dispersion, and then you'll end up with nonlinear Schrödinger itself. So usually you get KdV when you started off with a system with a non-trivial dispersion relation and scale x so that all high-order derivatives go into the epsilon, and you are only left with a first-order derivative. So that's actually a generic sort of hand-wavy argument that you'll see in a lot of papers, that we're looking for a KdV model because our dispersion relation omega of k has a power series, it looks like something times k plus something times k cubed plus something times k to the 5. Let me now scale x so that k cubed is small and the dispersion relation at order 1 looks like k. And I've got a k cube at the next order. I'm setting myself up for finding KdV. If I kept the k cubed and the k to the 5th and all of that stuff at the first order, I'm really sort of setting myself up for a nonlinear Schrödinger. Go back to the discussion yesterday we had of omega double prime being 0 or not. Right? And of course, when you say something is 0, you really mean 0 up to order epsilon. Any statement that equals 0 is actually an equal order epsilon. Okay. All right, so at the next order, we end up with L eta 1 U1 plus df d tau 1 1 plus f 3 derivatives plus this and that, where the traveling coordinate is this, and the time, the slow time, is tau. Okay, so you basically just plug in what you have into this expression. Each x derivative turns out into a xi derivative. U and eta are basically the same function, f. Because if you look at the form, what we have, u and eta both look like f. So you get the x squared, and then the time derivative will act on the tau to give me this slow time derivative. Right? So then I have all of that moved onto the right-hand side for my Fredholm alternative step. Right? So I have L operator acting on something equals known stuff. known stuff, but I just don't know how f evolved on the timescale tau. All right. The Fredholm alternative says the right-hand side should be perpendicular to the adjoint, to the null space of the adjoint. The adjoint and the original operator have the same null space. So that means the right-hand side should be perpendicular to the null space of the original operator. The null space of the original operator consists of any function times 1, 1, and any function x plus t times 1 minus 1. All of these functions that appear are functions of x minus t. I mean, they're functions of tau, but they're all, at this order, functions of x minus t. So all of this can be clubbed to one vector with two components that have functions of x minus t. Clearly, I don't want that. I don't want to have an arbitrary function of x minus t times the vector 1, 1. And evidently, I have a component in that direction. Right? Everyone sees that I have a component in that direction. I mean, certainly this guy is. And this split it off into functions. So if you keep this in the first term component, keep that in the second component, both have an f prime. You'll get a 2 and a 1 there. The vector 2, 1 has a component in the direction 1, 1. Similarly, the vector 1, 0 has a component in the direction 1, 1. So all of this looks like a sum of functions that depend on x minus t times vectors that have components along 1, 1. Okay? So all of that is a problem to deal with. And how are we going to deal with it? Well, we have to say it's perpendicular to such things. So we'll multiply by an arbitrary function of x minus t and take the inner product with the vector 1, 1 and integrate. Right? So let psi of c be an arbitrary function of c. Then the Fredholm alternative imposes psi 1, 1 should be perpendicular to everything I had in the right-hand side. Right? So I'll take the Euclidean inner product and multiply by psi and integrate and I end up with the scalar condition 2f tau plus f xc over 3 plus 3f f xc dx dt is 0. Right? If you want, you can write this guy as an x minus t. So this condition needs to hold. The function psi is completely arbitrary. So you can always choose it such that, suppose this function is positive somewhere, choose psi to be positive there. Suppose this function is negative somewhere, choose psi to be negative there. So you can sort of rig it so that the left-hand side can be, if this thing changes in sign, I can always make it non-zero. So the only way this could be 0 for arbitrary psi is if the following is true. And this is Korteweg de Vries. Right? So our condition is whatever we have as this arbitrary initial profile should suddenly start changing in time according to the dynamics prescribed by this equation. Okay? Note once again, just as in the original problem of the ODE we discussed, we started off with something that was 2 pi periodic and then added a perturbation and ended up with something that could be slightly different period. Evidently, the time dynamics I get here doesn't have to be, again, 2 pi periodic. I mean, first of all, it's an evolution on a longer time scale, tau. And the evolution is what it is. And so it doesn't have to obey, again, a 2 pi periodicity. It'll be something else. So in this case, we haven't introduced any new spatial scales, so the spatial periodicity can remain, although it's in the xi variable. So in the original x variable, it's got stretched, because xi is epsilon x. So if epsilon x is 2 pi periodic, then x is 2 pi by epsilon periodic. Right? So again, this whole idea that not only do your amplitudes change, your periods change as well. You get this new modulation. Any questions about this? We're all good? So this is definitely an easier calculation than the one I did yesterday. And it sort of falls out in a much more straightforward way. And sort of contrast this with the fact that the essential difference is the fact that the dispersion relation of the linear operator is simpler. Okay? Notice even in the case of the Schrödinger equation we did yesterday when we derived it, we did have translation at one order. And then that thing got modulated by something else. Here again, we have translation, but we get it modulated by something else. Okay? Once again, what is epsilon? Tied to a physical number, h by L squared, but also tied to sort of how you want things to evolve in time. Right? It sort of tells you the time period of the change of the profile. It's of order epsilon. Yeah? Any questions before I move on? Yes? Yes. So everything works precisely the same way if I had taken G. If I had taken G, I'd have G of x plus t, the vector 1 minus 1. Once again, I'll get something. I'll let it evolve on a slow time. And then once again, I'll get an equation of this form. I think that sign changes to a minus. Things go backward, as they should. And everything else sort of remains the same. This now represents the wave traveling to the left. You can also say, what happens if I chose the arbitrary initial condition of a wave traveling to the left and a wave traveling to the right? Okay, so what would have happened? What would have happened is when you substituted here, you'd get functions that are functions of x plus t and functions that are functions of x minus t as well. And because of this nonlinearity, you'd get a function that's a product of a function of x plus t and a product of a function of x minus t. So you'd get single functions of this form. Basically, you'd get an f squared, an fg, and a g squared. Right? Now, which are the terms that cause problem? It's the terms that are purely functions of x plus t or x minus t times a suitable vector. So the mixed term is not a problem. It's not in the null space of the adjoint. Something that's a function of both x minus t and x plus t is actually a function of x and t. And hence, you are allowed to keep it on the right-hand side. It's like the higher harmonics we got. So for the other problems, when we got e to the 3 theta, we were like, yeah, that's fine. Similarly, the function of both x plus t and x minus t can remain on the right-hand side. It's only the things that are functions of x plus t alone or x minus t alone, which means the analysis I've done is exactly the answer you'd get, just by considering x plus t alone and x minus t alone. I don't have to worry about the interaction term. The interaction term will certainly change the answer, but it won't change that conclusion, which is to say, you will not have a coupled KdV, coupling waves going to the right and left. That should make sense. The wave's going to the right, the other one's going to the left. You're waiting a long time, tau. Why on earth are they still talking to one another? So the interaction can only happen at short time, and then they propagate away, and then they don't talk to one another, and they sort of are well modeled by these type of equations when you are well separated. Similar thing happens to the wave equation in general. Right? In the wave equation, yeah, there's a period of time when the two waves are talking to one another, but if you wait long enough, then it's just a wave traveling to the right and it's just a wave traveling to the left. Right? So there's no interaction after a while. Yeah. No. So if you think about it, higher order is going to only be an epsilon tau. It's going to be an even longer time scale. So it's been even more time since they had their initial interaction. So it's even less likely that they will actually see that. So you should ask the question, where is the information of the interaction hidden? And that's actually, in some sense, to be the initial condition for this problem. The initial condition for this problem is the outcome of an interaction. It's not necessarily the initial condition of the order 1 problem. Right? So there's like some complicated mess, and two waves pop out. It's the wave profile that came out of the interaction that you should honestly use as an initial condition over here. But unfortunately, you may not know that, because to know that, you have to pass through the interaction. And that might be a complicated thing, so you're like, nah, I don't want to do that, I'll just do something else. Right? So that's an important point. And I want to emphasize, for each eigenvalue, I get a KdV. Which is to say, if I had an n by n system here, for each distinct eigenvalue, I have a distinct speed. So if I wait long enough and the speeds are different, then they're not talking to one another. They're just propagating in their own direction at their own speed, and they're all well separated from one another. So how can you get coupled KdV? Repeated eigenvalues. So if the speeds are the same, then even on a longer time scale, they're still talking to one another. So it goes back to the question of, okay, now that you have repeated eigenvalues, do you have repeated eigenvectors? Because if you don't have, if you have independent eigenvectors, maybe they're traveling at the same speed, but they're going in different directions. So they're still not talking. So what's the really, the case to worry about is repeated eigenvalues and lack of eigenvectors. So you have generalized eigenvectors. Then you can have, for a certain time period, an interaction between two waves traveling in the same direction. Maybe after a long time, they will also decouple. But the interaction can last longer than the original order 1 timescale. And I mean, these are also really useful qualitative statements that you can go to an experimentalist and say, okay, set up a system, some noise should happen initially, beautiful waves should pop out in different directions with different speeds, and if you rig your parameters appropriately, then two waves should talk to each other for a longer time and then decouple. So those type of qualitative statements you can at least make at this level, even if you can't make all of this rigorous. Right, so saying that solutions to this problem are good approximations to the original problem, that's a separate question. But at the very least, you can get an idea of how to select experimental parameters to see something interesting. And that's really just an eigenvalue calculation. Right? So if this is your system, this matrix, that's all you're trying to rig up. And then you just let the system evolve. Right? It will be order some epsilon for some time period. At longer time periods, the error will grow unless you include higher order corrections. So if you want the perfect solution, you need to continue this process for higher and higher order. So if you stop this, then it'll only be good up to some time. Maybe that time is on order 1 over epsilon or 1 over epsilon squared, but it's still a finite time. Yes, so on some 1 over epsilon squared timescale, this approximation need not be good anymore. Yeah. So the only type of theorems you ever get to prove are, this is a good approximation on some timescale. Beyond that timescale, this is not a good approximation. That would be the naive guess. Right? That would be the naive guess, that you're at least approximating things up to order epsilon. So 1 over epsilon squared is, so you will have an error of order epsilon squared up to time 1 over epsilon squared. That's the naive thing that you can sort of hope for, and that's the kind of theorem that you would try to prove. And more interesting would be to say, okay, beyond that timescale, there is an error, but hopefully the error is only a phase error and not an amplitude error, which is to say that I'm only off by a phase difference from the true solution, not that my amplitude is off. So I'm capturing the energy, I'm just getting the t equals 0, the clock, I'm getting that wrong. So that would be a much nicer theorem, and sometimes you can prove something like that. Yeah. Right. Yeah, so you can certainly think of perturbations to this operator over here. Right? So you can have some non-diagonal terms over there. Have at it. So then all that happens is you get some extra terms over here. Cool. Well and good. What that does mean is you'll get some additional terms here. Fair enough. You'll get some additional linear terms. First derivatives in Xi. That's fine. Yeah. Psi to be a function of both of these. Nothing much really changes because if this is a function of the other traveling wave coordinate, remember this is an arbitrary function that you get to pick however you want. So then you can pick it precisely to make this integral 0. Another physical way of thinking about it is, if waves are traveling in opposite directions, their support is different. So the bump is here and the bump is there. So where this bump is, there's 0 value here. Where this bump is, there's 0 value there. So the product is 0. That's sort of like a hand-wavy way to think about it. But the more rigorous way to think about it is, yeah, I get to pick a psi. Is there a psi that can make that condition go to 0? And the point is, in the case where psi is traveling in the same direction, you don't get to do that unless you set the term in the brackets to 0. If, on the other hand, it's got a component traveling in the other direction, who cares? They don't even have a common area of support, so naturally they're orthogonal. Right? That's the logic. Okay. Any other questions? Yeah. No. Just think of this as there's an original function that's a function of x minus t and epsilon t, and I've defined a coordinate change. I'm calling this xi, and I'm calling that tau. So when a time derivative occurs, it can act on the xi bit, but that won't give me an order epsilon term. That would have been in the previous order. So the time derivative acting on the next one, the epsilon t, is what gives rise to this df d tau. And when I act it with x derivatives, That's equivalent to me acting it with xi derivatives, right? Yeah, we're all good? Okay, so then let's make life more interesting. Let's pick up, in some sense, where we left this problem, which is with KdV. Okay, so I want to discuss an example that sort of emphasizes a point that perturbation theory, the way I've presented it, I've usually said it's a linear operator plus an epsilon times a nonlinear operator. And I want to give you an example where that's not the case. I'll start off with a nonlinear operator plus epsilon times a linear operator. Okay? So the point is, perturbation theory is like you do a perturbation about a good point. Finding good points for linear operators is easy. Finding equilibrium points or zeros for nonlinear operators is generically hard. But sometimes it's easy. And in those cases, you can perturb those nonlinear operators with whatever kind of perturbation you want, linear or nonlinear. Okay, so I'll take this KdV. I'll write it in a preferred form. And I'll add a small damping term. So epsilon is positive. And u is a real valued function, right? And so we'll call this the damped KdV model. Oftentimes, this arises as the perturbation theory model from a higher order model. So like I got KdV from Boussinesg, suppose I had Boussinesg with small friction. Then a model that I may get is this damped KdV. Now the epsilon here is not the previous epsilon. The epsilon here is a small parameter telling me what my friction is. Okay? All right, so here, epsilon equals 0 leads to a nonlinear PDE. So if I were to do perturbation theory, if I were to set up u equal u of 0 plus epsilon u1 plus so on, to find u0, I need to solve a nonlinear PDE. Right? Now, okay, maybe I could solve the initial value problem and keep all initial conditions, that entire function, as a slowly varying function of time. That's not fun because I can't do anything explicit. I can't get that map from initial data to the final solution explicitly, asterisk, unless I know inverse scattering theory, in which case I can, but then that goes off on a completely different tangent. So I want to keep life easy, but still sort of interesting. And one way to do it is to notice there exist special solutions to KdV, specifically traveling waves. That is, solutions of the form x minus 4 kappa squared t, where kappa is a real number. 4 is for convenience. Okay? So I can consider traveling wave solutions of that form to the unperturbed problem. Okay? So if I wrote down what that is, I end up with minus 4 kappa squared f prime plus 6 f prime plus f triple prime. Now, what kind of traveling waves am I interested in? Maybe I'm interested in those traveling waves such that u goes to 0 as x tends to plus or minus infinity for all time. So I'm interested in sort of like lump solutions, right? So there's a bump here and it goes off to 0. So can I solve this nonlinear ODE with this type of a boundary condition that f goes to 0 at plus or minus infinity for xi? And it turns out that's actually easy to do. Johnson, Ablowitz, maybe Hunter, but certainly Johnson and Ablowitz have the calculation of how to go from here to that, where xi is now this frame of reference. Right? Note, in the terms of the previous problem, we are in a traveling frame of reference in the traveling frame of reference. The original xi was a traveling frame of reference x minus t. Now I am traveling in the coordinate frame xi minus 4 kappa squared tau. So I'm in a traveling frame of reference in the traveling frame of reference. Or I'm in a different traveling frame of reference. Speeds have added. Okay? So this is a solution to the unperturbed problem. Right? So u equals f of u of xt is f of xi equals 2 kappa squared sech squared kappa xi is a solution for every kappa. So we've got a class of solutions, an arbitrary parameter for our base problem. And I'm going to do perturbation theory. So what am I going to say? That which was a constant is now going to depend on time. What's the constant? Kappa. Think of it as the k in e to the ikx. Right? I mean, we had this free parameter k, and I introduced new spatial periods and temporal periods, and I let the amplitude, which was a function of k, depend slowly on time. Now I have a parameter. I'm going to let that parameter change slowly on time. That's my only degree of freedom. Right? So I have 2 kappa squared sech squared k xi, and I'm going to set up a perturbation series. So if we set up u equals this, our order 1 problem is the following. Which has a solution right? There's our solution. And so before we go to the order epsilon problem, let's make this a function of tau. What is tau? A slow time. Why did I choose epsilon t? Because I know at the next order I'm going to get this contribution from the epsilon over here. And so I'm just going to modulate my time. Easiest thing I could do. I could modulate other things. Unless I have a reason to, I shouldn't. So I'll just do the easiest possible thing, which is to allow time to change on a slow scale, which is to say this kappa, which is the amplitude, the speed, as well as the width of the solution to change slowly. Okay? So now what's the order epsilon problem? So sorry? Yes? Oh, it's because if you put a 6 here, it's easy, and you want the kappa here, you need to put the 4 kappa squared there. You can parameterize however you want. If you put the C here, if you put kappa here, then this quantity changes appropriately to a root kappa. Don't want to see roots parameterized with respect to this. That's the only reason. Question? Are you talking about order epsilon? Okay, let me write down the order epsilon equation. This equation? Yes? Oh, so I'm interested in, so I said there are special solutions to KDV, which is the unperturbed problem. That is epsilon equals 0. And I'm interested in that because I know at order 1 I have to solve precisely this equation. And I don't want to solve the general PDE, I just want to work with a special class of solutions. And the special class I'm working with are traveling waves, which are traveling with this speed, which is precisely this equation. By the way, there are many special classes of solutions to KDV. I'm working with a very specific set. Now the order 1, kappa squared UC 1 plus 6 DDC U0 U1 plus U1 minus U0 minus dd tau of U0. Right, so the time derivative will give me an extra term on the right that I've taken onto the right-hand side, and I'll get this linear differential operator acting on U1. But it's not a constant coefficient operator because I started off with a nonlinear problem and I wanted to find a non-trivial solution. So I end up with a variable coefficient operator. Variable coefficient linear operator. So if we write this as yes. No, I'm constrained because I don't know how to do many things. I could have chosen the arbitrary initial condition and found the solution map and then said the arbitrary initial condition should vary in time. But I cannot write it down explicitly. There is a procedure that allows me to integrate this equation called inverse scattering, but I shouldn't work with the initial conditions, then I should work with something else called the scattering data. I don't want to bring any of those complications into this lesson, so I'm working with something far easier just to highlight the fact that your bits problem need not be linear. And by the way, the fact that I chose KDV, I could have chosen any nonlinear scalar PDE and asked for its traveling wave solutions. So integrability at this level has not played a role. So even the fact that I worked with KDV doesn't. I could have had a different power here. I could have had different sorts of derivatives. The logic is the same. So what is the linear operator L? It's this minus 4 kappa squared dxc plus 6 dxc u0 plus dxc dxc dxc. Right? U0 is known to you, and this is the linear operator you have. So this is a linear operator acting on functions of xi which vanish at plus or minus infinity. Right? That was our traveling wave solution. That's what we're interested in. So this is a linear operator L acting on this space. So an inner product is, let me just do it with FG. Just the usual simple inner product. I have to choose something what? Are you worried about rate of decay? So for instance, if I chose both F and G in L2, a priori, I have not made any assumption, and that's equivalent to me never mentioning which Sobolev space I was working in for the other stuff. So just to make you comfortable, let's work with, we want solutions that rapidly decay at infinity. Rapidly meaning however fast you want, it decays. Okay? All right, so with this definition of the inner product, the adjoint can simply be given L dagger to be 4 kappa squared dxc minus 6 u0 dxc minus dxc xc. So when I do the integration by parts, the derivative goes, and then that's just a multiplication. Right? So L dagger looks precisely like that. And it's L dagger's null space that we're interested in, because that's what this combination should be perpendicular to. Right? So we want the null space of L dagger. Note, L dagger I can write in terms of products of operators as 4 kappa squared minus 6 u naught minus dxc xc times dxc. So I just decomposed the operator, pulled out a derivative on the right. And the reason I did that is because now I can recognize a Schrodinger operator and a derivative operator. So I could start playing games. I want the null space of the full operator. Let me try find the null space of the Schrodinger operator, which is to say I go read a book. Someone tells me if the potential looks like this, these are what the eigenvalues are. And then I say, well, what about that extra derivative? Well, if I work in the space of zero average functions on L2, then I'm good to go. So basically find the null space of the Schrodinger operator that you have there, and then set one of those eigenfunctions, suppose it has zero average, solve the equation derivative of a function equals the zero average eigenfunction. There's your entire spectra. Right? So there are ways to cheat for this problem. Suppose you didn't want to cheat, suppose you had a more complicated problem, well then this is a legitimately difficult question, which is to say what's the spectrum of a variable coefficient differential operator? So then you have to pick up another book and read spectra of linear operators. So you need a lot more functional analysis, you need tools, the buzzwords are Evans functions, so on and so forth, that you can sort of exploit to get an idea of this. There are good references. If you have questions, feel free to ask me after the lecture. I can point you to good references for these things. However, let's continue this sort of cheating way of doing stuff and make an observation. The observation you want to make is L dagger and this equation have something in common. In particular, L dagger acting on U naught is 4 kappa squared U naught C minus 6 U naught U E minus U naught 3 derivatives is 0. So the base solution I had is literally in the null space of the adjoint. Right? That part actually is fairly generic in that if you tried it with another nonlinear traveling wave type of equation, you'd see this type of behavior again. Why? Because this is a quadratic nonlinearity that you linearized. And so then you'll almost always get an operator that looks like this with the U0, U1. And then when you take a adjoint, you'll get that. All of that stuff is fairly generic. Okay? Quite generic, actually. Okay, so that means I've actually found an element in the null space. Right? Great. So I'm just going to multiply the right-hand side by the function U0 and integrate and set that equal to 0. That's my Fredholm alternative. Things, the right-hand side should be perpendicular to things in the null space. I found an element in the null space. I haven't told you it's the only element in the null space. That's where you need some extra piece of information. You shouldn't be surprised you need an extra piece of information. You started off trying to do a harder problem. You need some extra piece of information. But at the very least, the formal calculation, this part works out. And so at the very least, formally, you can impose the Fredholm alternative to obtain as the condition. Right? That much I can certainly do. I don't need the extra minus. Everyone has a minus. Minus goes out the integral equals 0. Okay? We can actually make some progress. As it turns out, computing the tau derivative is relatively easy. So what is du0 d tau? It's dd tau 4 kappa squared of tau sech squared kappa times c. Right? Yeah. Yes. Still, it will work. Still, it'll work because it'll be the associated linearization where here you'll have one lower power of u, and then when you throw the derivative onto the other side and you multiply by a u, you'll get the same thing again. It's fairly genetic. In fact, so I should give credit. So this stuff is coming from the book of Ablowitz and Seeger, based on work by Kaup and Newell in 1978. They do it in one section for this problem. The very next section, they put an arbitrary power p here and do it for that. So, and then the very next section, they put u double x here without the minus sign. So you can do all kinds of interesting stuff. Where does it fail? So fail I would say the real failure is whether the result is good for all time. Yeah. Yeah, yeah. Yeah. Yeah, yeah. Not really, no. I want to say it's actually a generic feature. I mean, the best way to do it is pick an arbitrary f of u and do the calculation. And I think that's the case. I think that's the case. Because they do it for modified KdV and higher order powers as well. And the breakdown doesn't occur in the inability to do the calculation. The breakdown occurs in the goodness of the approximation itself. Although that breakdown is visible at the level of perturbation theory. So you can actually see that breakdown as well. It's got something to do with the fact that higher powers will have a focusing instability that will sort of make blow up more likely to occur. All right, so one thing I can do is write this the following way. So if I take a tau derivative, sorry, is that 4 kappa squared? Yeah, no, that's 2 kappa squared. Right, so then this is 4 kappa sech squared kappa xi times d kappa d tau plus 2 kappa squared dd tau sech squared kappa xi. That's just product rule. This first term, I'm going to multiply by an extra kappa and divide by an extra kappa so that I get 2 u0 by kappa d tau. So I just multiply divided by a kappa to precisely get exactly that term. Over here, I'm going to play an even trickier game. So I need to take tau derivatives. Instead, what I'm going to do is take xi derivatives and then replace that appropriately by a u0. So if, okay, so instead of taking a tau derivative, what would happen? By chain rule, it's basically take a kappa derivative and multiply by d kappa d tau. Taking a kappa derivative of this is equivalent to taking a xi derivative of this and then suitably multiplying by a kappa. Because if I take a xi derivative, the kappa comes out. So when you combine all of that, and this is something that I recommend you convince yourself of, you end up with 1 over kappa d kappa d tau. The real reason you want to do this is certain integrals become super easy to do. Okay? So there's a bit of algebraic manipulation to go from here to here, but you can convince yourself that that's completely kosher. So then the orthogonality condition, which is u of 0 times u of 0 plus 1 over kappa d kappa d tau times 2 u of 0 plus xi u0 xi. D xi is 0. The advantage is I never actually have to do the integral. So if I multiply everything out, I have an integral of u0 squared. And then I've got another integral of 2 u0 squared. And then I've got an integral of u0 xi DDC, do integration by parts. And then that'll turn into U0 squared. Right? So if you combine this term and that last term, it's a derivative of a squared. Throw the derivative onto this. You get a minus sign with a half. 2 minus a half will be 3. 3 by 2, right? So then all of this turns into a very nice expression. 1 over kappa d tau is negative 2/3. Kappa gets to come outside the integral because it's an integral with respect to c, and this is a slowly varying object. So then you end up with a fairly simple ODE to solve for kappa. Kappa exponentially decays at the rate 2 by 3 tau, right? E to the minus 2 by 3 tau. There's an initial value of kappa naught. And then once you've got that, you can just plug it in over here. So our solution, I haven't found out what U1 is, but up to order epsilon, I've got how the soliton changes. And how does the soliton change? Well, this kappa parameter has to exponentially decay. It has to get smaller. If you look at what happens, that means the amplitude decays. That means it gets wider and it gets slower because the speed is 4 kappa squared. So the amplitude decays, it gets slower, and it gets fatter all at the same time, right? And so at this level, you've already got a nice experimental prediction. Someone has a soliton, you say, well, yeah, so it should get slower, fatter, smaller. And then we can start analyzing this. Of course, once you've got this particular Fredholm alternative condition true, you can try to actually solve, where is this, my order 1 equation. You can try to solve this differential equation. Okay? This is still a variable coefficient differential equation, so it takes some amount of work, but as I mentioned in the book by Ablowitz and Seeger, they actually give you the solution to the U1 problem. They also give you references to a whole bunch of works where they discuss all these kinds of traveling wave problems and see what the perturbation should look like. So this is usually called the sort of dispersion that's kicked up by the fact that you've got a sort of a damping term. So because of this damping term, you don't have an integrable problem. You don't have the original traveling wave anymore. So whatever you have will break up into a traveling wave and something else, some other noise. And then that noise will propagate at somehow. And that's exactly what this U1 is. So if you want more details of this problem, I haven't fleshed out all the details, but if you want more details, feel to look up the book by Ablowitz and Seeger. Yeah? Okay, I want to definitely stop at this point, so I'm happy to take any questions that people have. Yes. So it says kappa doesn't change at that time scale. So the question you're asking is, if I don't have this damping term, and I still go ahead and do perturbation theory, right? So specifically, I do perturbations to this traveling wave, this soliton, because I'm still taking the same base state. So then what the question you're really asking is what's usually called the question of stability. Is the traveling wave stable when you add an initial condition perturbation? The one reason why we see the formal calculation indicate kappa is a constant is because solitons are actually stable. So it just passes through the radiation, which is to say U1 exists, doesn't change the form of the soliton. Now, of course, if U1 is large enough, then something funny happens. But U1 being large is technically not allowed in the realm of perturbation theory because you really want this to be a small term compared to this. But if you kept epsilon order 1, then you can have an initial perturbation that itself kicks up a soliton or a traveling wave, and then something funny can happen, in which case it's a slightly more complicated interaction, but not too much in that the shape of the soliton doesn't change, but its position where it would have been without interacting changes, which is to say there's a phase shift. And I haven't really talked about the fact that there's an extra degree parameter that I could have done. It's kappa times xi minus xi naught. That's an extra free parameter that you have, and that's the one that actually changes. And so you can sort of detect that within the realm of perturbation theory. Yeah. But yeah, you're really asking then a question about the stability of the traveling wave. And the fact that d kappa d tau is 0 is not too surprising. These waves are stable, so they don't change. You have a question? Mm-hmm. Why did I put an epsilon there? Sorry, say that again. I didn't hear. You should ask Urvashi and Manas. So there's a problem they're working on where they have this KdV with some parameter, I guess we call it B. They have that problem to analyze. And C is always smaller than B. B may or may not be small. Some other people have looked at what happens when B is small, and the analysis they did was pretty much comparing these type of solitons, especially the damped one. And so where do these numbers come from? It comes from where does that KdV come from? And so that particular KdV that I've written comes from actually a system of coupled nonlinear Schrodinger type equations with an additional thing. Don't ask me anymore. It involves physics. I don't know. Why did epsilon get chosen as the Greek character? I guess there's a story. I mean, I don't know. All I know is I had a friend in graduate school who I knew wrote a homework exam where he replaced epsilon and capital N in his entire homework for a math proof. So capital N was a small number, and epsilon was an integer. He got a lot of points deducted on the homework by the TA. The TA was not having any of this. It was like epsilon is always a small number. So I don't have a story. I guess that's the only story I have for you, if that's good enough. Yeah. Yeah. Oh, for sure. I mean, if you have an invertible operator, that's a good thing, because then you have no condition and everything can be solved. Right? So you get a unique solution. You don't have an arbitrariness. You don't have a degree of freedom. You don't have any of those problems. So yeah, I mean, I'm discussing non-invertible operators because that's actually the more interesting case. The case of invertible operators is maybe you've seen it, maybe you've done something like a Newton's method and it converges. Every operator you took at that case was close to being invertible. Otherwise, it wouldn't have converged. Typically, when you see in a Newton iteration divide by 0 error, that's a non-invertible operator. You divide it by a 0 eigenvalue at some stage. So when a nonlinear equation has a linearization that's invertible, usually you call that the implicit function theorem. We can solve for the unknown uniquely without an arbitrariness. When the operator is non-invertible, it becomes interesting, and I've sort of discussed these type of things. No, I don't want to confuse. I don't want to conflate those terms. No. Yeah. Any other questions? All right, great. We're done. Thank you very much.